Hello and welcome to this video. I'll just start by apologizing that I have some background sound behind me. I have a generator running, so that's some background sound. I do apologize. I hope it doesn't affect the audio too much in this. In this video, I want to start just taking a couple of questions and trying to solve them. The whole idea is to just serve as kind of practice for you as you prepare for your exam. So basically just running through a couple of questions. I'll take the first one in this video and hopefully there'll be a couple of others in subsequent videos. So in this video we have a question. We have a transfer function that we're given. There's a claim that is made that this transfer function is for a low pass filter. Now, how does a low pass filter work? I know you remember this. A low pass filter does not attenuate low frequency signals significantly, but attenuates high frequency signals significantly. So one way we can test, now this is not a foolproof test, but one way we can try to show that this transfer function represents a low pass filter is to supply a low frequency signal and then supply a high frequency signal, or at least supply two signals, one with a frequency that is much higher than the other, and from that we can tell that we can see which gets attenuated more. Now it's not a foolproof test. It's not an exhaustive test, because if we test with two signals, that doesn't prove that with the entire spectrum of signals that you can send in, it is only going to pass low frequency signals. It is very possible it's a band stop filter, in which case the high frequency signal just happens to be within the stop band, and if you go to higher frequencies than that, it will pass those frequencies. But that is a kind of outside the scope of this course. In your part 5 first semester, you will take a course where you will talk about bode plots, BODE plots. Some people call them bode plots. I think most people pronounce them bode plots, but BODE, I prefer to just call them bode plots. It sounds sweeter for me. So with bode plots, you can actually look at the frequency response of the system, and then you can tell straight off from the plots whether it's a low pass filter, high pass filter, or whatever it is. But let's take this system. We're given this transfer function, and we're to check whether or not it is a low pass filter by supplying two signals, sine t and sine 100t. 100t obviously being of a much higher frequency than sine t. Here your omega is 1 radian per second, whereas here it is 100 radians per second. So this has a much higher frequency, at least 100 times higher frequency than this. So we're going to supply this to your system. Now, just in case you're interested, topics we'll cover in this example include transfer function, final value theorem, inverse Laplace transform solving system, partial fractions, and transient response of systems. So let's get right to it. First, I'll start by something we don't have to do, but which it's always a good idea to do because it helps you to visualize the system. So let's just go ahead and visualize the system. We have a system here. It is defined by a transfer function. Transfer function is 1 over s plus 0.1, and then it has an output. The output in this case is c. Nope, not c. The output. Well, let me just check what the output was. V naught. Okay. So the output is V naught of S, and the input is Vi of S. Okay, now I think you know this, but for the fun of it, let's just go ahead and write this. The output is equal to your transfer function, 1 over S plus 0.1, multiplied by whatever your input, the Laplace transform of your input, whatever that is. This gives us our output. So since we have this, let's go ahead and solve the system. Now, once we have this expression on the right, we can find the inverse Laplace transform. Taking the inverse Laplace transform of this will give us V naught of t. So if you want, we could say that our V naught of t, which is what we want to find, is the inverse Laplace transform of Vi of s divided by s plus 0.1. Okay, but now let's talk about Vi of s. What is Vi of s? So we're given two signals. The first signal is a low frequency signal that has omega being equal to 1. So starting from that system where you have okay, that should be V, your input signal, the first input signal I want to deal with is sine t. Now for this system, your Vi of s is simply equal to, remember, omega over s squared plus omega squared. Omega in this case is 1. That's 1 over s squared plus 1 squared. Okay, so that's plus 1. So this is our VI. Now this means that our output V naught will simply be equal to, well, maybe not simply, but will be equal to 1 all over transfer function S plus 0.1, and then our VI of S squared plus 1. Looking at this second part now, this first part is easy to deal with. We have a real negative root, that's fine. This second part, what are the roots? Real, complex, imaginary? Well, taking a look at this, if you try your b squared and your 4ac, b squared minus 4ac is negative, or your b squared is less than 4ac, in which case this system, you have complex roots or imaginary roots. So let's go ahead and find expand this to partial fraction. V naught of s is equal to 1 over s plus 0.1 multiplied by s squared plus 1. This is equal to, using partial fractions, we're assuming that will give us s plus 0.1 plus, because it's complex roots, you have bs plus c over s squared plus 1. If we put them together into a single fraction, you have a into s squared plus 1 plus bs plus c into, let's give myself some space on the right. Oops. So we have into s plus 0.1. All of this divided by s plus 0.1 into s squared plus 1. Now, why we're doing this is that we want to solve for v of t. Now, let me pause at this point and kind of back up a little bit. So I want to back up to just before we found the inverse Laplace transform. Should we, or before we started going to partial fractions in a bit to find the inverse Laplace transform, should we bother doing this at all? Okay, let's not break the thoughts. Let me come back to that thought in a little bit. Instead, let's go ahead and finish this off. Excuse me. So this tells me that 1 is equal to our numerator over here. Our numerator is a s squared plus a plus bs squared plus cs. Let's go to the right a little bit to see what else is there. Plus, what have I left out? 0.1 bs plus 0.1 c. Okay, so this is the expression we have, and now we could equate left and right hand sides. We get that a plus b is equal to 0, which implies that my b is equal to negative a. We have that coefficients of s, 0.1 b plus c is equal to 0. That's this term and that term. That means that our c is equal to negative 0.1 b. That's fine. And let's now take the constant terms. We have a plus 0.1 c is equal to 1. On this side we have a constant term as well, so that's equal to 1. C, we know is negative 0.1 b, so that means that a minus 0.01 b is equal to 1. B is related to a, they are negatives of each other, so we have 1.01 a is equal to 1. I hope you can see that this now became plus 0.01 a, so added them together. In other words, we have that our a is equal to 1 divided by 1.01. Okay, so this is what we have as our a. Once we have our a, then it means we have our b. B is simply the negative of a, which is equal to minus 1 over 1.01, and our c is equal to the negative 0.1 of b. So that is equal to, take whatever you have in b to find the negative of that, so it's 0.1 over 1.01. so that's same thing as saying 1 divided by 10.1. Okay, that's 0.1 over 1.01, and that we could write like this. So we have our partial fraction. If you want to scroll up to just see what we had earlier on. So that now gives us what our v naught of s. Remember, we're trying to find for v naught of s. So v naught of s we could write out as being a 1 over 1.01 divided by s plus 0.1 plus bs plus c. Bs. Now what I'll do is my bs plus c, I'll separate them into two separate fractions. So that will now give me bs over So that's minus 1 over 1.01 s divided by s squared. Okay, let's just scroll down a bit. I think this is getting ridiculous. So s squared plus 1, and then I now have my c as a separate fraction, 1 over 10.1 divided by s squared plus 1. By now you should have enough experience with inverse Laplace transforms to be able to solve this without doing too much gymnastics. So we're trying to find the inverse Laplace transform of v naught of s. That gives us, for this first expression, constant 1 over 1, or the coefficient 1 over 1.01 e to the power of minus 0.1 t. Okay, we get that straight up by looking at this. This expression, we have s over s squared plus 1. Okay, so subtract coefficient 1 over 1.01. S over s squared plus 1 is cosine of t, plus we need omega over s squared plus omega squared. So constant to be 1 over, sorry, coefficient 10.1, 1 over 10.1 sine of t. So we found our inverse Laplace transform, and now we could look at this expression and we want to determine, is this significantly, or how well is this attenuated? What's the maximum, what's the minimum value of this? Remember, your input was sine t. Your output, what is your output? What's the magnitude of what's the maximum value and what's the minimum value of your sine of your output? Determining that, you can determine how much your signal was attenuated. Now, looking at this expression here, as time tends towards infinity, okay, so if we are looking for, so let's kind of back up a little bit. When an input signal is supplied to is applied to a system, you will have two responses from the system. I want to be careful. Okay, let me rephrase it. You have one response from the system, but that response can be divided into two segments. The first segment is called the transient response. The second segment is called the steady state response. Now, the transient response is what happens while when your system has not yet settled. So take a simple example. If you jump into, or if you carry if you drop, I want to pick a good example. Let's say you had a bucket of water, a bucket that was half full of water, and you got what item is large? This is a bad example. You got a laptop and dropped it in the bucket of water. Forgive that example, it's a stupid example, but you got a bucket or a laptop and dropped it inside a bucket of water. You're trying to test Archimedes' principle to see by how much volume the water level will rise. Now, when you did that, would you take the reading of the water in the bucket immediately? No, you wait until the water settles, because when you initially drop in the laptop, you have the water rise and fall and rise and fall. You have a number of waves being created in the water. Think of that as your transient response. After a while, all the waves is settled down and the water now becomes steady. The water level becomes steady. That is your steady state response. At that point, you can now take your reading. So if we want to determine whether or not this system is attenuating a signal, we have to wait for the steady state response. So we let all the transients die out. Now, one way to make all the transients die out is just simply to check the time. If you want, is just find the limits of your system. Excuse me, your limit of your system as time tends towards infinity. So we find the limit of your V naught as time tends towards infinity. That gives us our steady state response. Now, we don't have to wait for an infinitely long amount of time to determine your steady state response, but generally speaking, the limit as time tends towards infinity gives us our steady state response. Okay, that will definitely give us our steady state response. Now, looking at this expression, it reminds us that we have something called the final value theorem. And with the final value theorem, we actually did not need to find the inverse Laplace transform of your V naught of t. If we want to use the final value theorem, once we have the Laplace transform of V naught of t, we could just use that directly to find our the final value if the conditions are right. So what does final value theorem say? Final value theorem says that the limit of a function as time tends towards infinity is equal to the limit of its transfer function, that's limit of v naught of s, as s tends towards 0. This is what the final value theorem says. Now, there are some caveats. We'll talk about that in a moment. Let's just assume that we decide to use this straight up for our system. Will this give us the answer? The answer is no, it will not give us a correct answer, but let's go ahead and test this out. Sorry, I left something out here. This should be the limit as s tends towards 0 of s v naught of s multiplied by your Laplace transform of the actual function. So what we're trying to do is to find the limit as s tends towards 0 of, remember what we had here, your v naught of s, we had 1 over something. Now I don't want to write the numerator, so we had s plus 0.1, I believe it is, s squared plus 1. In our numerator, we simply had 1, but what we're looking for here is s multiplied by that, so we'll have s in our numerator. Now let's find this limit. Find the limit as s tends towards 0. In this case, you can just slot in 0 wherever you see an s. So that gives us 0 over 0 plus 0.1, 0.1 multiplied by 0 plus 1. So, and that gives us 0. So steady state response here, we're getting it as 0. Is this answer correct? Well, it looks correct, but is it actually correct? To try to answer the question whether or not it's correct, let's look at this inverse Laplace transform that we got just here. In other words, let's try to find this same limit, but now in the time domain. I do apologize, my pen seems to have frozen a little bit, so I'm trying to encourage it to start working once again. Okay, yeah, it's back. Good. So let's try to find this same limit, but now in the time domain. So if you try to find the limit of this expression as time heads towards infinity, so for this first expression here, it's straightforward. As time heads towards infinity, this term goes to 0. Okay, so as time heads towards infinity, this term goes to 0. That's good. That leaves us with two terms, cosine of t and sine of t. Do these have a specific value? No. As time keeps on increasing, all you just have is this keeps on oscillating. This keeps on moving in sinusoidal form. This is also oscillating in sinusoidal form. So what we end up with, as time heads towards infinity, we end up with a sinusoidal signal. We don't end up with a constant. We don't end up with 0. We end up with a sinusoidal signal. This 0, in a way, you could say is the average energy you have in here, in this signal. But in reality, what you have is not 0. What you have is a sinusoidal signal as time tends towards infinity. So what happened to our final value theorem? Is the final value theorem flawed? The answer is no. The final value theorem requires that you must have two things. You must have real, or rather, let's take that again. You must have roots, poles, the poles of the system. Now, the poles of the system are the roots of your denominator of your transfer function. The roots of the denominator. Okay, so in this case, for your v naught of s, the roots of the denominator are your poles. The poles must have negative real parts. Now, I apologize for my writing here. Okay, they must have negative real parts, or rather, let me say and, not an or now, and not more than one pole on the j omega axis. So you can't have more than one pole on the j omega axis. Your poles must have negative real parts, and if you have any of them that doesn't have a negative real part, it can be on the j omega axis, but it must not be more than one that you have on the j omega axis. In our case, what do we have? We have one pole with a negative real part. That's good, so satisfies the first criterion. But then the second criterion says we must have not more than one on the j omega axis. Here we have two on the j omega axis, and that gives us a problem. We cannot use the final value theorem in this particular case. So we cannot use this final value theorem for this system. Not saying we should never use the final value theorem, but I'm simply saying that this final value theorem does not work for this particular system. Sorry, my pen froze along the way, and yeah, so let's hope it doesn't freeze again. What I should probably do is just break this rectangle so that in case there's a mistake, I don't have to redraw the entire thing. Okay, good. So we cannot use this because we don't satisfy both criteria. So instead, let us go on to work in a time domain. So, or let's just go ahead and draw the transient response of this system. let's draw the transient response of this system. So let's say we had our amplitude and we had our time axis. The first term, exponential term, is an exponentially decaying term. It starts from 1 over 1.01 and then it dies out. It dies out towards 0. Okay, I'll just stop there. So it starts from the maximum term 1.01 and then dies out to 0 as time heads towards infinity. Second term here, cosine of t, but then it has an amplitude of 1 over 1.01. So we start from, say, somewhere at about here, that's minus 1 over 1.01. And then let me just put some markers down here that will help me to sketch, even though I do apologize, my sketching will not be the best here, most likely. So start from there, we go up here. Now just assume what you can see is a sinusoidal signal. Has a maximum point at that marker. It comes down here. Again, just assume that this is a perfect sinusoid. It's not easy to draw with a pen. And some people say a bad workman always blames his tools. Okay, so let's stop there. So this is our cosine signal, and our sinusoidal signal is 1 over 10.1 is positive. So if we have a maximum of somewhere about there, the initial value will be 0. So if we start from 0 to go to a maximum of 1 over 10.1, and then it comes back to 0, and then it goes down to a minimum of minus 1 over 10.1, goes back to 0, it goes to a maximum of 1 over 10.1, back to 0, and then back towards the minimum. Okay, so this is what you end up having, and your final response is the sum of these two. If you try to do a sum of the two, what you end up with is still a sinusoidal signal. So what you end up with when you add those two signals will just simply be a sinusoidal signal. If you could check what the values would be, the maximum value may not be at, say, pi over 2, pi over 4, sorry, pi over 2, pi over 4, 3 pi over 2, 2 pi. It may not, the maximum and minimum may not happen to fall exactly on those markers. However, what you end up with is a sinusoidal signal. Now, what's the maximum and the minimum you have? The maximum amplitude and minimum amplitude you have for these signals? It looks to be somewhere at about 1 over 1.01 and minus 1 over 1.01. Okay, so we know the amplitude when we have this signal with frequency omega is equal to 1. Those are the amplitudes. Now let's take the second scenario. V naught of t is equal to sine of 100t. We supply this to our system. Let's find the Laplace transform of this. This gives us 100 squared omega, that should be 100, not 100 squared. 100 over omega s squared plus omega squared, which is s squared plus 100 squared. And that tells me, oh, sorry, do I apologize. This is supposed to be VI. VI of t is equal to that. VI of s is equal to this. And so my V naught of s will now be equal to my transfer function multiplied by the input signal. So that's s plus 0.1 into s squared plus 100 squared. I could write it as 10,000, but I feel it's a little easier to write 100 squared. Okay, so we have this expression here. We're going to need to take this into partial fractions as well. A over s plus 0.1 plus bs plus c over s squared plus 1, which tells me my numerator will be a into this should be 100 squared. Okay, so we're good. Into s squared plus 100 squared plus bs plus c into s plus 0.1. I just don't feel like scrolling to the right. I do apologize. Okay, let's I don't have to scroll right and left, so please, I hope you could see that reasonably. At least you know what is supposed to be there. S plus 0.1 and s squared plus 100 squared. Equate the numerators, and I'll just skip a step here. I hope you can see that a plus b will be equal to 0, which tells me, like we had before, b is equal to negative a. Coefficients of s, we have 0.1b plus c is equal to 0, c is equal to minus 0.1b. and constants. We have 100 being equal to 100 squared a plus 0.1 c. Like we did earlier on, we can express my c as being equal to, since b is the negative of a, then our c, if you want your c, is simply equal to 0.1 of a. So we could put that in, which we convert to c is equal to 0.1 of a. So that means that our a will be equal to 100 divided by 100 squared, 10,000.01. This now becomes 0.01. Okay, so this gives us our a. Once we have our a, our b is the negative of that, which is simply negative 100 divided by 10,000.01, and our c is equal to 0.1 of our a, so that will be 10 divided by 10,000.01. Let's go ahead and finish this up. So that tells me that my v naught of s is equal to v naught of s 100 over 10,000.01 divided by s plus 0.1 minus b 100 over 10,000.01 divided by s squared plus 100 squared plus c is 10 over 10,000.01 divided by s squared plus 100 squared. Okay, so this third term is one that could be a little challenging, in the sense that we want to express this as k multiplied by omega over s squared plus omega squared. S squared plus omega squared is here. If we place omega in the numerator, then if we have 100 in the numerator and here, then a multiplier by that, we need to multiply that by 0.1 divided by 10,000.01 to get our k omega. Okay, so we could find the inverse Laplace transform of this as 100 divided by 10,000.01 e to the power of minus 0.1 t minus, sorry, it just occurring to me, I'm hoping I didn't make a mistake earlier on in my, okay, that's fine. I was not sure if I left out the 0.1 in my exponential earlier on. Okay, so minus 100 divided by 10,000.01 multiplied by, oh, I left s out of this, my apologies, multiplied by the cosine of 100t plus this, we need this to be omega, so that gives me 0.1 divided by 10,000.01. So that will now be multiplied by 100 over s squared plus omega squared. So in the time domain, that becomes sine of 100t. If you compare this term to this term, obviously this is very, very small, and this will not contribute much. Now, once again, as time heads towards infinity, this will head towards 0. So we are left with just a sinusoidal term, and in this case, what we are left with is mostly just the cosine term. Now, what we're interested in is the maximum. V naught max will be equal to 100 over 10,000.01, and our V naught min is equal to minus 100 over 10,000.01. So this is what you have when inputs is equal to sine of 100t. Now, if you check this amplitude compared to the previous amplitude, you see that this is a whole lot smaller. So we have shown rather, that the higher frequency signal is attenuated more than the lower frequency signal. Now, if you don't mind, let me just go ahead and show the step response of this particular system. I want to show the step response of this particular system. So let's define this system. Let's just call it sys. We could give it any name, but let's just say our system is defined by a transfer function. In Matlab, this is how you define a transfer function. Your numerator, you have just a constant. In your denominator, we put in the coefficients. So what we had was s plus 0.1. So we could just simply put in the coefficients and you have this in here. By the way, you know this in Matlab, you define, many times when you're defining an expression or a polynomial, you often just use the coefficients alone. So that's what we do here. So that's our system. Let's now find the step response of this particular system. Find step response of this system now. Okay, so I'll plot that in a moment, but just to come back here, and so just to mention that we have shown that this system is actually a low pass filter. So this system here defined here is actually a low pass filter. Now, just before I show the, or just to, as a refresher, remember that a low pass filter is a filter, or let's say if, okay, is a filter that can be expressed by generally by a transfer function that is something of this nature, constant divided by s thou plus 1. Okay, constant divided by s thou plus 1. This is the transfer function of a low pass filter, generally speaking. That's transfer function of a low pass filter. Now, you could express this obviously as k divided by thou divided by s plus 1 over thou. Now, if you look at this expression and you look at this expression, if you equate them, it shows you that your 1 over thou is equal to 0.1. In other words, your thou has to be 10 seconds. Thou being a time constant, okay? So your thou has to be 10 seconds. And if we have k over thou, what is k? What's the gain of this system? Thou is 10, then k over 10 is equal to 1. That means that the gain of this system is 10. Okay, so bear those two things in mind. We have a time constant of 10 seconds and the gain is 10. Now let's go to Matlab and let's go ahead and plot the step response. So step of the system, and if you plot the step response, give a moment. I should probably have issued this command while I was going back to talk there. Okay, so there we are. So this is the step response of the system. I'll turn on the grid just so you see this now. The maximum value you can get here, note, is 10. Okay, the maximum value you get is 10. We had a unit step input signal. The input signal is a unit step, and the output we see has a magnitude, and in steady state, the magnitude is 10. So that shows us the gain of the system is 10. Now, let me just click on this plot and drag the mouse. Hopefully to respond shortly. Okay, drag the mouse. I'm looking for the time constant. Now, if the maximum value is 10, we're looking for where we are about 6.3. Okay, and we're about 6.3 at time 10 seconds. That's what we have over here, 10 seconds. And so this shows once again that the time constant of the system is 10 seconds, which is exactly what we were expecting. So I hope you've enjoyed this video. See you in the next one.